Today's problem is submitted by a viewer, and it says, a small bullet of mass m is fired into a block of wood of mass capital M, which is at rest. The speed of the bullet on entering the block is u. Its trajectory within the block is a horizontal straight line, and the resistance to the bullet's motion is capital R, which is constant. The block is fixed. The bullet travels a distance a inside the block before coming to rest. Find an expression for a in terms of m, u, and capital R. And then there's a second part. Instead, the block is free to move on a smooth horizontal table. The bullet travels a distance b inside the block before coming to rest relative to the block, at which time the block has moved a distance c on the table. Find expressions for b and c in terms of capital M, m, and a. Okay, so it's just a mechanics question. The only thing I'm not 100% sure on with the interpretation is exactly what it means to say that the resistance to the bullet's motion is R. I assume that that means there is a force of R applied to the bullet in the opposite direction of its travel. That's what I'm going to assume. I'm not going to assume that this is some sort of coefficient of friction, because I think that would change things a lot. Like if the force were proportional to the velocity or something like that, that would make things a little bit more difficult. Okay. So I have a bullet with mass m. It's traveling in this direction with a speed of u. And the block is fixed. So a block of mass capital M. Let's say that, let's indicate that it's fixed to a particular point like this. The resistance is R, which is constant. And the bullet travels a distance of A inside the block before coming to rest. Find an expression for A in terms of M, U, and R. Okay, so the force, if I have that the direction to the right is a positive orientation, then the force on the bullet is equal to negative R. So F is equal to the mass M. Oh man, I mean, I'll say that the acceleration then is capital A, which is equal to negative R. So the acceleration is equal to negative R over M. This means that the amount of time between the impact of the bullet and the time it stops, so delta V is equal to the acceleration times delta t. So what I want to compute is delta t. This is the amount of time it takes the bullet to slow down to a halt. This is delta V divided by A. So delta t is equal to and what is delta V? Well, the initial velocity is u and the final velocity is 0. So u times m over it's negative u times, right? The change in velocity is negative u. The initial velocity is u and the final velocity is 0. So delta V is equal to negative u. And we divide by A. So this gives m divided by capital R. Minus signs cancel. So that's the amount of time that the bullet travels inside the block for. Now the distance it travels, which has been called A, this is an integral of the velocity, which is a function of t, dt, and we integrate this from 0 up to delta t. Okay, and what is vt? This is equal to u plus a times t. So vt is equal to the initial velocity u plus the acceleration times the amount of time acceleration has happened for, which is negative r over m times t. Okay, so we want to integrate this. A is equal to the integral from 0, and delta t was um over r, of vt, u minus r over mt dt. Okay, so the distance is equal to the integral from 0, over r. Oops, I want to do this as u times t minus r t squared over 2m evaluated at 0 and over r. Okay, so the distance that the bullet travels in the block is, are these all going to cancel? U squared m over 2r. So a question like this, once you set up a coordinate system for everything, you know, I've said that the right direction is positive, and then I've just written out all the equations of motion. Newton's second law, we're told that the force has a magnitude of r, and of course it applies in the opposite direction to the bullet's traveling, so it comes with a negative sign. And then I've just used, you know, once we have that written down, the rest is just purely mathematics. You know, by definition, the distance that the bullet travels is the integral of its velocity. So there we go. You know, and again, by the convention I laid out at the beginning, a positive velocity means the bullet's traveling to the right. A positive value of of a means the bullet has moved from, you know, I've also, I guess, implicitly said that this is like a I've in my mind I was assuming that this point here is the origin. So this is where the position is equal to 0, and then we have positive position in that direction. So just crunching out the mathematics, and this all works like that. Great. Okay, now we have quite a bit of a different thing going on. Its trajectory within the block is a horizontal straight line, and the resistance to the bullet's motion is r, which is constant. The block is free to move on a smooth horizontal table. The bullet travels a distance b inside the block before coming to rest relative to the block, at which time the block has moved a distance c on the table. Find expressions for b and c in terms of capital M, little m, and a. I assume we will also need the initial velocity u and the resistance r to compute these quantities b and c. The main way I intend on formulating this, I'm going to set up a coordinate system for everything again. I will have quantities representing the velocity of the bullet at any time, the velocity of the block at any time. That will allow me to write down relations for the position of the bullet in absolute terms and the position of the block in absolute terms. And conservation of momentum is going to be the important relation that sort of ties things together. Okay, so this is going to be the position, should I call it X? The position 0, okay? And positive positions are going to go in this direction. So the bullet enters the block at this point, and it travels with velocity vb, I'll call it vbt for the velocity of the bullet. And we also have, oh man, like we'll have v capital BT, I suppose. V capital BT will be the velocity of the block. Now I'm still going to assume that the force on the bullet is equal to negative r, even though, you know, it is the block itself which is applying the force to the bullet, and these two things are like changing speeds with each other. You know, the question says that the resistance to the bullet's motion is capital R, which is constant. So I'm going to assume this. This means that the force on the block capital B is equal to positive R. Again, we're assuming that the smooth horizontal table means that the block is not resisted at all by the table itself. It slides frictionless. Maybe we won't need to use conservation of momentum, by the way. We might just be able to put these two things together. So the force on the bullet is negative R. The force on the block is positive R. So the acceleration of the bullet is the same as it was before. It'll be negative R over little m. That's the acceleration of the bullet. The acceleration of the block is going to be R over capital M. Delta T is going to be the same quantity. I am doing everything in terms of, you know, relative to the stationary table. So relative to this point 0. If this is the acceleration of the bullet relative to that 0 point, then I have the velocity of the bullet in terms of, you know, absolute, a fixed frame of reference. So the velocity of the bullet is going to be the same as it was before. It's going to be u minus rt over m. And the velocity of the block, well, the initial velocity is 0. So this is just going to be rt over capital M. Okay. And the amount of time that changes is going to be the same. That's when the bullet stops. Oh, hold on, there's a problem. The bullet doesn't stop because the block will continue moving. Yeah, so delta t is going to be a little different this time, because while the bullet is slowing down, the block is speeding up. Think about just, you know, the physics of this happening. If you shoot a block, the bullet will slow down as soon as it enters the block, but the bullet will be pushing the block forward. And the question says the bullet travels a distance little b inside the block before coming to rest relative to the block. So to be at rest relative to the block means that these two velocities are equal. So if I set these velocities equal to each other, I have u minus rt over m is equal to rt over capital M. So u is equal to rt 1 over m plus 1 over capital M. Let's make this a little more clear. Okay, so u is equal to rt m plus capital M over m capital M. So this is the time at which the two velocities are equal. So when we do our integration again, we're going to integrate from 0 up to this t. I'll call this t star. This is how long it takes for the bullet to come to rest relative to the block. Okay, and we want, so what simply all I'm going to do is find, in absolute terms, relative to the initial point of entry, how far does the bullet move? How far does the block move? And then we should be able to find how far the bullet moves inside the block. Okay, so the position of the bullet at time t star is equal to the integral from 0 to t star of vbt dt velocity of the bullet is u minus capital R t over m dt. Okay, so we have u t star minus r t star over 2m t star squared, sorry. So the position of the bullet at the time of interest is u squared m capital M over r m plus capital M minus r over 2m times this thing squared, u squared m squared capital M squared over r squared m plus m squared. See if this simplifies a little bit. Doesn't simplify that much, but I get 2 u squared m squared m plus u squared m capital M squared over 2r m plus capital M squared. I think I did that right. Okay, so let's put a star there. That's the absolute position of the bullet. So we want to find the absolute position also of the block at time t star, which is the integral from 0 to t star velocity of the block, which is the integral from 0 to t star of capital RT over capital M. This is r t star squared over 2 capital M and what is t star again? T star is that it's over r m plus m. Okay, so we've got u squared, little m squared, capital M squared, r over 2 capital M r squared m plus capital M squared so the position of the block is u squared m squared capital M divided by 2r m plus capital M squared. Right. So we have the position of the bullet, the position of the block. This here, in fact, is the quantity C that was asked for, the distance that the block moves on the table. And the quantity little b should be the amount that the bullet moves inside the block is the total distance the bullet moves in total minus the distance that the block has moved. So quantity little b that we're asked for is going to be x sub b t star minus x sub capital B t star, which is, okay, let me just copy this. And we'll see if some stuff simplifies here. So we're subtracting u squared m squared capital M divided by 2r m plus capital M squared. So the denominator is already locked in for us, and we just lose one of those. So we get u squared m squared capital M plus u squared m capital M squared over 2r m plus capital M squared. Yeah. I think I did everything correct here. Again, you know, the assumption that I made about the force the block applies to the bullet, again, I'm just interpreting things the way it's written here. You know, I don't think this is exactly how the friction between the block and the bullet would work in reality, but it might be a pretty good enough approximation to what's happening in reality. I didn't actually end up using conservation of momentum anywhere, although this here is probably that I'm sure is equivalent to the conservation of momentum, that the force on the bullet is the negative of the force on the block. They're equal and in opposite directions. I don't, you know, most of the algebra here was pretty straightforward, so I hope I didn't make any mistakes, any arithmetic mistakes or anything like that. We should be able to do some sanity checks to see what happens, for example, as capital M goes to infinity. When capital M goes to infinity, this quantity goes to 0, right? We have a linear term divided by a quadratic term, and that makes sense. If the block is infinitely massive, then when you shoot it, it's not going to move at all. Also, when capital M goes to infinity, I would think that this quantity b is going to be the same as the result we solved for in the first part of the problem. So let's see if we can just figure this out by inspection. As capital N goes to infinity, we have an m squared there and an m squared there. We should end up with u squared m over 2r, and that sounds familiar. Yeah, u squared m over 2r. So at least as a sanity check, the expression we get at the end works in the limit for very large capital M. I wonder if there are other quick sanity checks that we could do. You know, as little m goes to 0, obviously nothing moves, like the bullet will stop instantly. This will be 0, and the block will not move at all. Are there any other limits we could take? I don't know. Something we do see is that the bullet, like this quantity here, the distance that the block moves, that is kind of contained within there. So the bullet moves a distance which is strictly greater than the distance that the block moves. Again, these are absolute distances relative to the fixed reference point, and that makes sense, right? As soon as the bullet enters the block, any movement that the block has forward the bullet sort of picks up that movement as well. So I mean, I hope that I interpreted everything in this question the way it was meant to. Maybe the viewer that submitted this can sort of confirm whether this is exactly the approach that was intended to be taken. I can't really see any other reasonable way of approaching this question, interpreting it in a different way. But really, the key to everything here was setting up a coordinate system at the very beginning. A lot of problems in mechanics that are sort of this type of level, set up a coordinate system, just instantly say, okay, I'm going to have the velocity of the bullet, velocity of the block. It might be tempting to have a quantity which is, the velocity of the bullet relative to the block at any point in time. I think that would be much more difficult to go through, because then, what is the acceleration of the bullet in that? So, you have a moving frame of reference, actually. Not only that, you have an accelerating frame of reference. So, the Newtonian mechanics just kind of breaks down completely. The laws of physics that you're used to wouldn't work in exactly the way you would expect. Just set up a fixed frame of reference, write down all the quantities relative to that fixed frame of reference, and once you write down Newton's laws of motion, well, this is Newton's, I don't even remember what the laws are numbered. This is Newton's third law, right? This is Newton's second law applied to both objects. And then just write down this is Newton's second law, but this here is the definition of the relationship between velocity and acceleration. If acceleration is constant, then velocity is going to be a linear function of time. And then the rest is just sort of crunching out the math. I guess another tricky part in this question was realizing that the point in time we're interested in is not when the bullet stops, because the bullet never stops. It's when the bullet stops relative to the block. But what does that mean? It means that the velocity of the block and the bullet are the same. And then you can solve for the value of t, which is necessary to put into these integrals. Yeah, that was a cool question. Had a lot of fun doing it. Thanks for watching.